Hey everybody, it's Ripley again. We're going to go ahead and finish up the material in Chapter 1, just to give you an idea. Again, this is going to be real heavy vocab-wise, so you might want to make some flashcards. You might want to revisit it. Remember, your textbook is a great resource that you can carry with you wherever you go, in absence of a Wi-Fi connection, if you can't get access to this video again. Okay? All right, but today we're going to start collecting some data. It's going to collect data. We're going to talk about the ways to do this. Okay. Now, I apologize for my rudimentary drawing, but if I would rather saw my foot off with a spoon than make another PowerPoint. Plus, I think it's more interesting to talk about it this way. Let's talk about the different ways that statisticians and scientists collect data and why they collect data. All right. First and foremost, there are two types of tools that statisticians use and that scientists use when they want to try and prove something with statistics. All right? First and foremost, there's something called an observational study. All right? Observational study is simply just an observation of past data. So we're looking at past data. It would be things like number of troops that were killed in the war in Afghanistan or the war in Iraq. It would be the average GPA of the class of 2012. Things of that nature. You're just observing. You're not doing anything at all. You're just looking at it and you're writing down the numbers, and then we do mathematical analysis on that. And I'm going to show you what that mathematical analysis entails. Now, I don't mean to present this as being a weaker thing to do numerically. It's just different. All right? The other is to do an experiment. All right? Now, let me tell you what an experiment involves, because experiments are really cool. An experiment simply involves, sorry about that, my pen's a little squishy, it simply involves a treatment. All right? And at its absolute simplest, let's do this first. I'm going to have one group, so this is sample A. All right? So I take a sample out of the population. Remember how that works. If this is the population, which is the set of all things that have a certain measurable characteristic, then what I do is I take a little group out of that, and this right here becomes my sample. Now, the way in which we grab that sample is really, really important. We'll go into that. We'll go into the best practices for that here shortly. But let me show you what happens back over here. All right, so here's the way an experiment works. So I've got sample A, and then I got sample B. All right, and sample A is just your rank and file, let's call it my control group. So we'll call these guys the control. And really, with the control group, what that implies is we do nothing. We just leave them alone. So do nothing. Let them do what they're going to do. Okay? And then with the experimental group, what we do is we apply the treatment to them. All right? And then we measure for differences. So, for example, let's say that we want to measure the effect of loud music on performance on an exam. Okay? So I would come over to my population of students taking a statistics exam. I would pull out a sample that would become my control group. I would pull out a sample that would become my treatment group, and then I would give them an exam. All right? The control group would be sitting in a room, a nice quiet room, standard issue. The treatment group would be sitting in a room with loud music playing. So there'd just be this god-awful, loud, whoops, lost my thingy. I'm terrible at drawing these, sorry. Loud music. And then what I would do is I would look at the effect that had on the performance on the exam. The control group, I'd take the average or whatever. I could do it graphically. We'll explain that down the road. Look at their average. I could look at the treatment group's average on the exam, and then I look for differences. Now, I think that we all intuitively think that the treatment group may do poorly, but you never can tell. And that's where we start getting into a lot of the more nuanced things that deal with statistical analysis. Okay? Now, like I said, I don't like to do PowerPoints. However, that said, we're launching into a vocabulary situation here, so I'm going to put some stuff up on a PowerPoint as well, just so we can blow through the vocab real quick, and it just makes it easier than having you sit there and have me write simple, random, sample. All right, which my handwriting is terrible. So bear with me. The PowerPoint will pop up here in just a sec, and you can enjoy that. And flash! We're in a PowerPoint production. Sorry about that, you guys. Okay, so let's talk about data collection and how to build your samples. There are three basic random samples that we have to think about here. The first is a simple random sample. The simple random sample, let me see if I can explain this. Let's say that I gather a sample of 5 kids to create a sample that I'm going to do an experiment on. Simple random sample says that that group of 5 kids, again, let's go with gifted kids, okay? That group of 5 kids has the exact same probability of being my sample as any other group of 5 kids. So it's the sample that is randomized. It's not the individual. So if I were to take one member out of the 5 kids and stick a different member in, that group of 5 kids has exactly the same probability of making it as my sample. All right? Now that's different from a random sample. In a random sample, every individual in the population has the exact same probability of being chosen to be part of the sample. There's a distinction there. Think of the simple random sample as the sample is what's being randomized versus just a random sample where the individual is being randomized. Then there's something called a probability sample. That's where each individual in the population has a probability which is known, but it's not necessarily the same probability for every individual in the group. And the reason we do stuff like that is, let's say that I'm trying to test some gifted kids, okay? And I know that my gifted population is 10% African American, 20% Asian, 50% Pacific Islander, and the rest are Caucasian. Then what I want to do is, I don't want to do a simple random sample with that, because if I'm trying to grab 5 kids, I might end up with 5 Caucasian kids, or I might end up with 5 African American kids, and I want my sample to reflect my population. So what I would do is I would tweak the probabilities that the Caucasians would get in, so that their probability of getting into the sample reflects what proportion of the population they truly are. All right, so just so you know. All right, other methods of sampling. Now let's talk about these. Some of these are good and some of these are bad. So we'll yap about them just a little bit here. Now there's systematic sampling. Systematic sampling, think of it this way. If I'm trying to sample the population of the United States, and I happen to have all their Social Security numbers, so I work for the Social Security Administration, and I'm just trying to get some information out there. And clearly maybe it's a pain in the butt for me to be able to try and completely randomize this. So what I do is I take my list of Social Security numbers, and I'm going to grab every 20th person. Okay? Well, clearly that's not a truly random sample, because every person doesn't have the same probability of getting in. But it's a real systematic way for me to gather data. Okay, that's systematic sampling. Convenient sampling, probably the worst of the sampling. I wrote it as the man on the corner. That's where you stand outside of your house and you gather data from people that come walking by you. Now, as you can probably tell, that's going to be a little bit biased, because the people that come by you are your neighbors, so they probably share, at least your socioeconomic status. They might share a lot of the same data that you're trying to gather. So that's a great way to create bias, not a wonderful way to sample. There's stratified sampling. Now, stratified sampling is kind of cool. This is where you take the population and you break it up into groups based on characteristics, and then we select those. Now, let me see if I can get this thing to work right here. I'm going to grab my ballpoint pen. Now, think about it this way. If I take all of the Think classes, and let's say that there are 4 Think classes, and I'm going on at any time. So you got the stat, and you got the history, and you've got the English, and then what else? You got the philosophy. So I'm going to break these guys up by class. I'm stratifying them based on classes. And then what I do is I grab a couple of people from here, a couple of people from here, a couple of people from here, and a couple of people from here. That's how stratified sampling works. So you bust them up into their strata, and then that guarantees that you have representation from each one of those strata. That's another way that we could do in that little race sample that I was talking to you guys about earlier. Excuse me. You could say I'm going to bust them up based on race. So you'd have your Caucasians, you'd have your Asians, you'd have your Pacific Islanders, your Caucasians, etc. Now cluster works the same way, except what we would do is we would say we're going to bust all of the classes up, and then we're going to randomly select one of these classes to be our sample. So we're going to take the entire group, and that becomes our sample. So rather than 2 from each one of the classes, we're going to take all 8 out of the stats class. Or we may take the entire stat class if the stat class happens to be 8. Okay? So those are other methods of sampling, some of which are pretty good and some of which aren't. Okay, we're going to go ahead and switch gears here and talk about experiments. But before we do an experiment, as it were, we're going to talk about a specific experiment. I want to make sure you got a little bit of vocab here. All right. The first term that we're going to talk about is replication, or replicating an experiment. Replicating an experiment means that you do the experiment on more than one subject. The subject is somebody who participates in the experiment, or you have the ability to repeat the experiment over and over and over. I'm going to talk a little bit about a way to teach calculus. We'll set up an experiment for teaching calculus here in a minute. So if I want to replicate my experiment, that means that if I'm going to use a different way to teach calculus, I'm going to use that on more than one person for obvious reasons. That single person may perform really well with the new method of teaching, and they may perform poorly. So we don't just want to take one data point, is basically what that says. Also, what would be nice is if I could duplicate that experiment over the course of, say, a number of semesters. All right? So that's replication. Let's talk about blinding. I'm sure you've heard this term before, but let's have a little chit-chat here for just a sec. All right, blinding is real simple. You basically blind people that are participating. You don't like throw acid in their eyes. That'd be against the law, painful. But you make it so that they don't know whether or not they're receiving the treatment or not. Okay, so in the case of the calculus experiment, if I've got students that I'm teaching calculus in a new way, in an innovative way, I don't want them to know that they're receiving a treatment, because you can get something called a treatment effect or a placebo effect if people think that they're getting a treatment and they're actually not getting it. Single blind means the subjects don't know if they're receiving the treatment or not. So you're sitting in my calculus class and you have no idea whether you're getting a new and innovative way or not. Double blinding means that both the subject and the person running the experiment, the people in interaction with the subjects, don't know who's getting a treatment. So if you're talking about a medical, like a pill experiment, the people giving the pills to the people to take don't know whether or not they're getting a placebo or they're getting the actual drug that they're trying to test. Now, in the calculus case, that it's impossible to double blind. I'm the one teaching the class. I know whether I'm teaching an innovative way of teaching calculus or if I'm teaching just a regular old. Okay? Controlling. Let's talk a little bit about controlling, because really controlling your experiment is the biggest challenge. It's the biggest hurdle that we have to overcome when we do statistics, when we do statistical research with experiments. At its absolute simplest, it's really ensuring that there is a control group. That's the first place that you start. There has to be a group that isn't receiving the treatment so that we have something to compare the treatment group with. That's the reason that we do that, is we are trying to control the effects of the treatment. If we see a difference in the two groups, we can say, okay, this probably happened as a result of the treatment, like in the calculus case, because I changed the way in which I teach calculus. That's the reason that I saw a change in the outcomes. What happens when we don't control properly is we get what are called confounding variables, and that's where the experimenter mistakes the cause of the difference between the two groups. Let me give you an example. Let's say that I have a first period calculus class and I have a fourth period calculus class. Here at the Davidson Academy, fourth period comes immediately after lunch. And I use the innovative way to teach calculus during fourth period, and I use the rank and file way to teach calculus during the first period. And then at the end of the semester, I compare the grades, and voila, behold, I have better performances on assessments in my fourth period class. Now, hopefully, your spidey sense is tingling here a little bit. There should be bells going off. It's like, wait a sec, Ripley, first period, kids are asleep. Maybe they're not paying attention. Fourth period's right after lunch. They got some exercise. They're a little more focused. They can pay attention. Exactly. I have confounded, or I have mistaken the cause of the difference in scores. I've confounded it with the time of day that the kids took versus the actual treatment effect, what the treatment did to the students. All right, that's confounding, and confounding is a major problem, and that's the reason that why we seek to control a lot of those things. And I'll give you some techniques for doing that. Okay. All right, so real quick, making a bomb-proof experiment or observational study. Remember, an observational study is we just observe stuff that's already happened, versus an experiment where you actually have to come up with a design and have all sorts of fun with it. Okay, which we'll get into here in just a sec. An observational study is make sure that you clearly define your population. You always want to make sure that you do that, and randomize your data as best that you can. Sometimes it's really, really difficult to truly randomize data that comes in. And then, of course, do good math. Sounds a little simple, but it's true. Don't screw up on your math. And especially in the age of computers, there's going to be a lot of software packages out there that'll spit out values, and we've all heard that garbage in, garbage out. If you don't know what you're doing, then you're not going to know what you're looking at when the computer gives you a number, and you may misinterpret it. Okay? For an experiment, it's a lot more complicated. You want to randomize members of both the control and treatment groups. You want to be able to replicate your experiment. All right? Think of replication. If you've done the replication properly, basically you could write up a set of instructions and pass it off to somebody like-minded, and they could do the exact same experiment. They may not get the same results, but they'll be able to do the exact same experiment. So that's a way to sort of simply replicate your experiment. You can describe it really easily how to replicate. Okay, blind your experiment as much as is practical. Sometimes it's not practical in the example that I gave you earlier. All right, and then of course watch out for confounding. When I say watch out for confounding, what I mean is always be real critical as you're designing your experiment, saying, okay, what else could cause this other than the treatment that I'm trying to prove caused a change? All right, is there anything else that could cause a change? Okay, all right, so you got a little bit of vocab. I'm going to go ahead and pop over to my tablet here, and we'll design an experiment. We'll talk a little bit for a few minutes about how to design that calculus experiment that I was talking about earlier, and then that'll be the end of the chapter. Again, I apologize for too much use of the PowerPoint, but we're going to get out of that here in a little bit. We'll have to endure a little bit more, but not so bad. All right, hope you enjoyed. I'll see you on the tablet. Hey everybody, we're back at the tablet. Let's do a quick little experimental design here. All right. Let's say that there are a grand total of, we've got a population of kids, and there's 1,000 of these kids taking calculus. All right, so I got 1,000 calculus kids. And what I want to do is I want to see the effect of an innovative way of teaching calculus. So let's say that I'm going to flip my classroom like I'm flipping with you guys, where I give the lecture material online, and then in class we just do mathematics, and we practice, and we get into some of the deeper level stuff. Okay. Now there's several ways that I can select my sample. I don't want to deal with all 1,000 kids, especially on a university campus. That's sort of a logistical nightmare because you got kids coming and going and doing all kinds of things. Okay. So let's say, just to keep it simple, let's say that I want to have 50 kids. I want 50 kids in my experimental, and then I want 50 kids in my control. Okay. All right, now one way to do this is called a completely randomized, let's go, completely randomized design, or experimental design. Okay, now the way that this works is really simple. It's actually the simplest of the things to do. However, unfortunately, it's not feasible. What we're going to do is we're going to take all 1,000 kids of these guys. We're going to assign them a number, and then, so I got 1,000 up here, and then I'm going to randomly select the kids to go 50 in here and 50 in here. This is, again, my experimental, and this is my control. All right, so I would number the kids 1 through 1,000. I'd pull out my fancy schmancy random number generator, and I start pushing numbers until I got 50 in the experimental and 50 in the control. You can probably see the problem with this. The problem with this is that if I do it in this way, is that I've got 1,000 kids that are spread across a number of classes that they may or may not have already registered for. So let's say of the 50 kids in here, that may be spread across a whole bunch of different sections or different classes. How are you going to teach to just those few kids that may be in one class and leave the other ones behind? So in this case, a completely randomized design doesn't work. Sometimes they do, but not necessarily, okay? So in this case, that's not going to work. Again, I can't teach to 3 of the kids in a 40-person class with my new and innovative way because they happen to have been selected for the experimental group, okay? So there's a way around that. What we do is we're going to do a randomized block design. Whoops, block design. All right, now here's what we're going to do. Let's say that I've got 50 kids and we're teaching big classes, so bear with me. Oops. We're going to have 10 classes every semester. All right, did I say 50 kids? I meant 1,000, et cetera, et cetera, et cetera. All right, so what we're doing is we're blocking the kids by the classes. This is class 1, this is class 2, etc., class 3, and then out here is class 10. And we're blocking them by their classes. And then what we do is we're going to randomly select which of these classes we're going to do the experiments on until we get up to 50 kids. And then we'll randomly select which of the kids out of those classes get included in the data. So let's say, just for giggles, that class 1 has, let's see, what do we got? Let's keep it simple. Class 1 has 100, whoops, not 1,000, sorry guys, has 100, 100 again, just to keep it simple, et cetera, all the way out to 100 each. I'm going to randomly select 2 of the classes, one of which is going to be, so let's say this guy gets selected, and let's say this guy gets selected. Okay? Then I'm going to randomly select which one's going to be the control and which one's going to be the experiment. So you take a random number from 1 to 10, pop it out, that becomes your experimental. The other one becomes your control. Okay? Remember, experimental gets the treatment. They'll get the new way of teaching. The control gets just the regular old, I'm going to lecture to you, you're going to go home and do your homework, et cetera, et cetera. All right? Now remember though, there's 100 in each one of these classes. So then what we do is, again, I only want 50 in each one of the, in each group when I'm doing this, in each of my samples. I would randomly select 50 of the kids to collect data from. Now the other 50 kids still take the class, they still get the information, but I don't use their data. All right? They have no idea that they're receiving a new and different treatment, but they're part of an experiment that they don't know about. Okay, now you're going to hear me say your spidey sense is probably tingling here. Sometimes you can get something that I affectionately call cross-pollination in an experiment, and this isn't actually in your book. But the problem is let's say that the kids in the experimental group really like the new way of doing things, and all of a sudden they start yapping. They start yapping about what's going on. Well, some of these control group kids are going to find out about it. Now, will that have an effect on your results? Will that have an effect on your data? Maybe. Maybe it doesn't. But that's something that definitely has to be addressed, because then we might see changes that we don't necessarily, that aren't necessarily accounted for by the treatment alone. And remember, we call that confounding. Confounding is muy malo. Okay? All right. Now, let's talk about a rigorously controlled experimental design. All right? It's pretty simple, really, at its roots. All right, so if what's going on here? Sorry, guys. A rigorously controlled design. A rigorously controlled design simply seeks to eliminate, maybe misspelled, eliminate confounding. And the way that this is typically done is by trying to get, remember I got my experimental, I got 50 kids in here, and I have my control. All right, and I got 50 kids in here. And the way in which you do this is, let's assume that we did the block design just like we did. The rigorously controlled design is kind of a secondary level. What I'm going to try and do is I'm going to try and make the experimental and the control group look as much alike as I possibly can. Maybe the same number of men and the same number of women in both of them. Maybe the same proportion ethnically, socioeconomically, et cetera, et cetera. So if I've got 50% Caucasians and 20% Asians and 30% African Americans in this group, in the experimental group, I want to try to do the same thing in this group. Now, you're probably realizing there's no way that you can control for everything. And you're absolutely correct. Control is an illusion, and it's very difficult to avoid confounding of any kind. But we seek to get as much control as we possibly can. Another way to do this, think of this as a tertiary level, is called a matched pair. A matched pair design. And this is another rigorously controlled design technique. Okay, matched pair design. And think about how much work something like this would take. I have my experimental group. I have my control group. All right, what I'm going to do is, let's say that I've got data value x1 over here. I want to make sure that I have data value x1 over here that looks as much like this guy as possible. In other words, if x1 over here is male, then x1 over here is going to be male. If x1 over here is African American, then x1 over here is going to be African American. If x1 over here got a, I don't know, a 680 on their SAT, optimally, x1 over here is going to have a 680 on their SAT. Can you see how much work something like this is going to take? A match pair design is a really difficult design to do, especially if I've got to do this for 50 students. There's no guarantee that out of these guys, when I blocked this, remember how I blocked it? There's no guarantee that, let's see, this was C4 and this is C5, that when C5 got selected, Class 5 and Class 2 got selected, that I'm going to have the ability to do a match pair design on this. There's just no way to control for that. All right, I mean, there could be out of the all, whoops, I don't know what just happened there. Out of all 1,000 kids, I may be able to pull 50 out of out of the experimental and 50 in the control that are closely matched. But a match pair design, in theory, matches perfectly, which of course we know that doesn't happen. Let me elaborate a little bit more on the match pair design. Okay, a really easy, whoa, I didn't like that at all. A really easy way to do a match pair design. Think about it. Think about this. Let's leave the calculus example for just a second. Let's see if a ibuprofen improves your headache. Okay, so I want to know if ibuprofen takes care of my headache. All right, so ignore all the confounding variables. We're not going to try and control too much, but we're going to do a match pair design. Watch how easily this works out. You take data value x1. This is my before. All right. Ouch. I have a headache. This thing really hurts. On a scale of 1 to 10, I'm going to give it a 7. All right. Then what I do is I'm still x1, but now I'm after. I've taken the pill. The treatment is the pill, and then I rank my score. Maybe the ibuprofen had no effect. Maybe I still have a 7. Maybe it helped a little bit. I have a 5. Or maybe it just killed it dead and I'm down to a 1. Notice, since it's me taking since it's me before I took the pill and me after I took the pill, I'm the same person. That's a perfect match pair design. Before and after procedures are fantastic because they give us the ability to match the pair because the individual is receiving the treatment. They have no treatment before and they have treatment after. Okay? All right, cool. Those are ways of controlling. Those are ways of trying to design experiments, some of which are practical, some of which are not. I'm going to talk about one more thing, excuse me, and then we'll be done for the chapter. I hope you enjoyed. It has to do with error. Now, error, I think, has been sort of ingrained in our brain as being bad, right? Well, that's not true in statistics. There's something called sampling error. Sampling error. All right, now let me show you how this works. Sampling error is simply the error that happens when measuring data. It's the difference between what you get and what you expected. So it's really, if you think about it, it's at its absolute simplest, it's the observed minus the expected. Whoops, expected. All right, absolute value because it's an error, of course. All right, so think about it this way. We know that the IQ scores are on a normal distribution, which we'll get into down the road. We know that their mean is 100 and their standard deviation is 15. All right? Let's say that I grab 10 students and I test their IQ. And those 10 students end up with an IQ of 108, an average. This is their average. So this is 10 subjects. All right? And this is an average. Now, there's a, God bless it, average. Okay? Now, there's a question here. Am I doing an experiment or am I doing an observational study? Well, think about that. I'm giving them an IQ test, but the IQ test is not meant to affect their IQs at all. It's simply a measurement of their IQs. So this is an observational study, because all I'm doing is pulling an IQ that in theory, I know there's lots of argument against this, but in theory already existed there. Now notice, this is different from this. Well, that's just due to random chance. That's the chance that I selected those 10 subjects and measured their IQ. Clearly 108 isn't 100, but that kind of error is to be expected. Now, let's say that my instrument with which I measured IQ was off. All right, it didn't measure it correctly, for better or for worse. Maybe it measured too low, maybe it measured too high. Maybe the results that it got were off. That's called non-sampling error. Non-sampling error. All right, now, this is bad. Muy malo. This is error that's simply due to, this is due to an error in sampling, in technique. Okay? So again, my IQ test in this case was dead wrong. It doesn't accurately measure. You know, it's kind of like the difference between taking an actual IQ and then going online and doing one of those goofy ones. Okay? All right, that's the end of the chapter. Tomorrow's a big day. It's your first day of class. Hopefully you took the time to look this over. I am always open to suggestions, comments, criticisms, as long as they're constructive. I would love to give you guys something that's useful and that you can keep coming back to and looking over. So I'll see you in class. Welcome to Stat 152, and I really look forward to working with you guys. Have a really good day.